Welcome back to Chemistry from Jay's House. So today we are still talking about gases. I know you're pretty shocked about that. I didn't collect homework, I didn't go over homework, but I know what you guys are thinking. Jay sure talks a lot, but what's the point? Let's go to the write the date. I believe this class is supposed to happen on the 19th. Again, if that date is wrong, write the correct date. So look at your phone, computer, whatever. Skip the line, go all the way left, right, the point. And the point today is, how are pressure and volume related to temperature in gases? So how are pressure and volume related to temperature? So we're going to be looking at these separately. We're going to look at pressure versus temperature, and then we're going to look at volume versus temperature. Okay? So it's actually two mini classes combined in one. How are pressure and temperature related, and then how are volume and temperature related? Well, no time like the present. There are no formal notes. There'll be formal notes tomorrow, but there are no formal notes today. So I'm going to write some stuff that's pretty important, but notice it's not black, which means it's not mandatory. And the first is the Gay-Lussac law. Gay-Lussac is a guy. It's a single guy. He's a hyphenated last name. He actually discovered this along with another person whose name I'm forgetting right now, unfortunately. And that is how pressure and temperature are related. And what he said is pressure and temperature are proportional. Now, technically, they are directly proportional, and we'll talk about that in just a minute. But Gay-Lussac was talking about specifically pressure and temperature. And again, that's one dude. He has had a hyphenated last name. He's long dead now. And then you have Charles' law. And what Charles found is that volume and temperature are also proportional. And again, they are directly proportional. And we'll talk about that in just a second, what directly proportional means. But Charles was looking at volume and temperature. And again, this is for gases. This doesn't relate to solids or liquids, only things in gaseous state. So what I could name the class is, what do Gay-Lussac's law and Charles's law state? But instead I wrote it that way. Well, I would pause the video and write that down because it's super important, and then come back. So pause. Okay, welcome back. So Gay-Lussac is a person, and he said that pressure and temperature were directly proportional. And proportional simply means as one increases, the other also increases. But that can be considered proportional, even though as one increases, as this increases a lot, this increases a little bit. That is a type of proportional. What directly proportional means is however much this goes up in lockstep, the exact same amount. So directly proportional means that they behave the exact same way. However much one lowers, the other lowers, and however much one raises, the other raises. So pressure and temperature are actually directly proportional. So numerically, If this doubles, this also doubles. If this drops by 5, this also drops by 5. That's what directly proportional means. So it's stronger than proportional. This should say directly proportional, but I find that if I write directly proportional, students get so wrapped up in, oh, what does directly proportional mean? That they totally forget that what we're really talking about is pressure and temperature, and don't worry about directly proportional. It just means that they go up the same amount, and it's not this kind of a thing, right? Okay. Pressure and temperature are directly proportional. Another thing you need to know is temperature is in Kelvin. So it has to be degrees Kelvin. So if we were going to do math, and we're not going to do math, lucky you, but if we were, it would have to be degrees Kelvin. So you would take all your temperature readings either in Kelvin, or you'd take them in Celsius and then add 273.15 to it to get the Kelvin temperature. But we're not actually going to do math with this. This is a conceptual class, so you don't really need to know this yet, but if you continue on in college, you will have to do math with it, and you'll have to do it with degrees Kelvin. So there it is. But what does this mean? Well, let's take a look. Let's say that we have a container. And it's a metal container. It's sealed, which means volume is not changing. The container's not getting bigger or smaller. It's just like an old bean can that's been sealed and used for science now. And underneath that bean can for science is a poorly drawn burner. So we got, you got some flames. Ooh. And we're heating up the bean can. Now, the bean can does have gas in it. And let's just say that that gas is air, so we don't have to, talk about weird gases like argon. Now, what's going to happen? Well, we know that already before we even light the flame, so before we even have a flame, we know that air is gaseous, that the particles inside the can are going crazy, and they're all going about the same amount of crazy, right? They're all basically the same temperature. I haven't been messing with the bean can. So all the particles, so each little dot there is one air particle, right? So that could be a nitrogen particle or nitrogen molecule. It could be an oxygen molecule, carbon dioxide molecule, whatever it is. It's a particle of air, and it's just bouncing around. Bing, 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 bing. And more or less, it doesn't matter if I'm looking at this one or that one or that one. They're basically all going the same amount because they're all at room temperature and they have basically the same amount of energy. Which means the pressure, and remember pressure is, let me change colors here. Pressure is this moment right here. Pressure is when the particle bangs against the can. How hard does it bang? That's what pressure is. How hard, and pressure is right here. Now this one that's just flying through, it's not really putting any pressure. That one's not putting any pressure on the can at this instant. Now, in a moment, it's going to, right? It's going to bing, or it might ding, 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 hit a couple air particles and then bang against the can here. But pressure only truly happens at these moments when it actually hits the side of the can. So the pressure right now is standard pressure at room temperature, whatever it is. I could take a reading, I could put a number, it could have a decimal, it could be super accurate, but what I'm really measuring is how hard are these air particles banging against the inside of the can. But what happens when I light my poorly drawn Bunsen burner? Ooh, what's going to happen now? Well, I know that heat increases, so the first thing I know is that when I light it, clearly the temperature is going to go up. That's why we light things on fire. Either to increase the heat or because people owe us money. So the temperature increases when I light this on fire. So I know in here, because it's right above the flame, the temperature is also increasing in here. But what does that mean? Oh, that's right. That means that the particles are getting more kinetic energy. So instead of going that fast, they are going to go that fast. And instead of going that fast, they are going to go that fast. And instead of going that fast, they're going to go that fast. And instead of banging against the can this hard, they're going to bang against the can harder. As these move around more, when they hit the can, when they actually bang against the edge of the can, they are going to bang harder. Why? Because I heated them up, giving them more kinetic energy, had them move more, and so when they actually hit the can here and here, so instead of banging this much, it's going to go bang, bang, bang. Oh my gosh, look at that. Look at all the kinetic energy it has right now, which means when the temperature increases, the pressure is also going to increase. Oh, okay. So what you're saying is when the temperature goes up, the pressure goes up. And when the temperature goes down, the pressure goes down. That sounds like they're proportional. And in fact, as long as you use the right units, they're actually directly proportional. So if this goes up this much, that goes up that much, right? If the temperature drops this much, the pressure would drop this much. Now, I totally believe that as the temperature increases, as I light the Bunsen burner, I totally believe that the pressure is going to increase. We're going to bang harder. But what if we lower the temperature? What if instead of raising the temperature, now we lower the temperature? So what if we put the whole thing in a refrigerator? Well, it's kind of hard to draw a refrigerator, so I'm just going to draw a poorly drawn ice cube, right? And we'll even give it a little ice cube sweat. Oh, and it'll make a little puddle. There we go. So that is an ice cube, since that's not super obvious from my drawing. And what's going to happen is that is going to supposedly cool this entire system. So imagine this is actually in a refrigerator, not just above a single ice cube. I'm just not that great an artist. So there it is. Now what's going to happen? As this ice cube is going to cool down the can. And what that means is when this bangs, it's actually going to ricochet slower. The can was hot, which means when the air hit the can, it, kind of got helped out. But now the can is cold. Now these air particles, instead of going this fast, they're going to go this fast. And instead of this fast, they're going to go this fast. And instead of banging this much, they're going to bang a lot less. Now, with the temperature dropping, the banging is going to be a lot less. And what do we call that? We call the banging against the can pressure. So if the temperature drops, the pressure does drop. And lo and behold, it's exactly what we expected. As the temperature changes, the pressure changes the exact same amount. So not only are they proportional, they are directly proportional, right? So again, this goes up by 3, that goes up by 3. This scales down by 0.572, this scales down by 0.572. They are directly proportional. Okay, and a guy named Gay-Lussac, along with somebody else who, tragically I'm forgetting badly, discovered all this for gases. As long as the temperature is in degrees Kelvin, you can do math with this, and it will work out perfectly. Ding! Okay, so I believe that pressure and temperature are done, and that we have found out that pressure is directly proportional to temperature using my poor drawing. Okay, now let's talk about volume and temperature. Okay, so what does volume and temperature? So now we're walking away from Gay-Lussac and his law, and we are going to go to Charles and his law. So what does Charles's law state? Oh, that's right. Charles' law, what he said is that volume and temperature are also proportional. Again, they are directly proportional. So you double one, you double the other. Okay, so we're talking volume and temperature. What does that mean? That's crazy. Now, this is usually drawn as like a canister with a plunger. I like balloons, so I like to draw mine as a balloon, but it requires a little bit of uh, a little bit of understanding, a little bit of suspension of reality, because we're going to heat this balloon. And usually when you heat balloons, they pop. So this is a science balloon that can't pop. It is made out of Kevlar rubber. That doesn't exist. It does. It totally does. Just, the government just doesn't want you to know about the Kevlar rubber that they use. No, there's no such thing as Kevlar rubber. But imagine this is made of something, of a rubber that can stretch and surprisingly doesn't pop when you put heat under it. So we're going to draw the same thing. We're going to talk about our particles. So we have little particles in here. Now, this balloon is not made out of helium. It's not flying away. It's actually just made out of my breath, and it is being anchored here to the wall. So I'll do a little plate. It's got a little plate holding it, and it's just anchored there. So it's not trying to fly away. It just has air particles. So it's got nitrogen particles and oxygen particles and carbon dioxide particles and trace amounts of other stuff like helium and hydrogen and all that good stuff. So we have these particles, and they, just like in our previous example, they are flying around, and because it's room temperature, they're basically all flying around the same amounts, right? They've been at the same temperature for a long time, and they bang into the balloon all over the place, and that's actually what gives the balloon its shape. So it's these moments right here that give the balloon its shape. But we're not worried about pressure, so I'm not going to draw pressure here. What we're worried about is volume. We're worried about how big the balloon is. Volume is what is the size of the three-dimensional shape that it takes. So if you've ever put Peeps in the microwave or thrown a marshmallow in a campfire, you notice that as it heats, it gets bigger. Why does it get bigger? I wonder if that's because volume and temperature are proportional. Let's find out if that's why. So here we go. I just have my balloon. It's balloon shaped. This is the room temp size for that balloon. And then I decide, hey, what if I put a poorly drawn Bunsen burner under it? I wonder what would happen. Well, first thing, I'm going to cut the string so that the string doesn't melt. No one wants to smell burnt hand-drawn string. It's really kind of a disgusting smell. And right now, before I light it, the particles are bouncing around room temperature amount, bing, 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 and making the balloon this big. Then I light it. Oh my goodness. Holy cow. Now what's going to happen? Well, just like in the bean can, the last part of the video, these things are going to move faster. The heat's going to give these more kinetic energy. So instead of going that fast, this guy is going to go that fast. Oh my gosh. And instead of banging this amount, this guy's going to bang that amount. And same thing with this guy. Instead of banging that much, he's going to bang that much. And what's going to end up happening is my Kevlar rubber balloon is actually going to grow. Because what happens? Why is the balloon this shape? Well, we have to not only think about the particles inside the balloon, we also have to think about air particles.